Right. We have another problem in two-dimensional forces. Here I attempted to draw a 18-wheeler perhaps, or a large vehicle that's driving up an incline at 10 degrees. And on the bed, or the flatbed, the back part of this large truck, there's a crate. That's the color-in portion here. Crate on the back of the bed. What we're trying to find is at what rate can the velocity of this car, of this truck, change, in other words, acceleration, the rate at which velocity changes. At what rate can this truck accelerate and avoid the crate slipping off of the back of the bed? Immediately when we see the incline here, and I see an object moving up the incline, I'm thinking almost exclusively of forces. Not thinking of kinematics. The only kinematics or motion quantity that were provided here, or that is even considered, is that of our maximum acceleration. But I know acceleration relates directly to forces, so if all I'm asked is about acceleration, trying to find the maximum acceleration that this truck can have as it maneuvers up this 10-degree incline, I know that acceleration is going to depend on the forces that are acting on this crate. So that we have our picture drawn and we have some sense of how to proceed, that is, using Newton's second law and forces, we'll begin that forces analysis using a free body diagram. We'll represent our crate with this dot, and now we need to draw the forces that are acting on this crate. We have, of course, weight, which is pointing straight down because this crate has some mass. There's the weight of the crate. We have the normal force of the flatbed that's pushing up against the crate. Because it's the normal force, it's perpendicular to the surface, so it's perpendicular to this incline. So we'll point it something like this way. There's our normal force. Because we're given a coefficient of static friction, we know that there is friction that exists between the crate, or the bottom of the crate, and the surface of the flatbed. If our crate is moving up the incline and accelerating up the incline, the force that's actually causing that acceleration is the static frictional force. That is the force that's accelerating our crate upwards. So that force is pointed up the incline. There's our force of static friction. And those are the three forces that are acting on our crate. A normal force existing between the surface of the flatbed pushing up on the crate, the weight of the crate because it has some mass, and the frictional force, that is the force that's actually accelerating the crate upwards and along the incline. You can get the same idea if you were to place a light object on top of a cloth and to drag that cloth along a table. That light object would travel with the cloth in the same direction that you're pulling it. It's the same idea here. The truck is in contact with the crate. Because it's in contact with the crate, there is some normal force. Because there's some normal force, then we have some frictional force. That frictional force is what is allowing the crate to continue to move forward. This is also the same idea as the friction between your shoes and the ground that allows you to move forward. That static frictional force is pointed in the same direction that you move. All right, now what we need to do is analyze this free body diagram using Newton's second law. We'll begin with our trick to reorient our axes, our x and y axis. So now we're going to have our x and y axis tilted at 10 degrees. So we're going to tilt at 10 degrees. So here is our new x-axis, or along the incline is our x-axis. We can call this positive x. And then perpendicular to the x-axis is our y-axis, or perpendicular to this incline, there's our y-axis. So this would be positive y. And here's positive x. All right, the advantage of doing this, and the reason we almost always do this in our forces in two dimensions circumstances is because originally, if we didn't tilt the axis, we have two forces, the normal and the frictional force, that would be in two dimensions, both x and y. Now that we've tilted our axis, we have normal force exclusively in y, frictional force exclusively in x, and the only force that's in two dimensions is the weight. Effectively, what this does is eliminate the amount of trigonometry that we have to do. All right, now we need to project the weight into its y and x components. There is the y component of the weight, and now we'll project the x component of the weight along the incline. There is our x component of the weight. We know that if we followed our incline all the way down, here would be our angle theta. So we can put this angle as well using some simple geometry right in this area right here. That is the same angle theta, or in our case, 10 degrees. We can expand this triangle right here to show the trigonometry. If I show weight directly downwards, I'll make it pretty big for us. And then we have perpendicular to the surface. Here's our weight in y, projected along the y-axis. Here's our weight in x, our weight projected along the x-axis. Here is our theta. If we know the weight, which weight is always equal to mg, I'll write that up top here. Weight is the mass times the gravitational field. Then I can find any of these other two components, the x and the y component. If I take the sine of theta is opposite over hypotenuse. The opposite side to this theta is weight in x. So that would be weight in x over hypotenuse, weight, which is mg. So we can conclude that weight in x is equal to, if we solve this simple equation, mg sine of theta. That's what our weight in x will be equal to. If we look at cosine of this angle, cosine of theta, that's adjacent over hypotenuse. Our adjacent side is weight in y. Our hypotenuse is the weight, which is mg. So we can conclude that weight in y is equal to mg cosine of theta. All right, back to our problem. That's our quick analysis of this vector triangle that we made here, the projections of y and x for the weight. We'll analyze the forces in the x and the y dimension here. What's happening in x and what's happening in y. If we look at the forces in the x dimension, there are two. We see the frictional force is one, frictional force, looking at our free body diagram. And the other force in the x dimension is the weight in x. Those are the two force vectors that are acting in the x dimension. They cause some acceleration in the x dimension, right? These forces are what contribute to some net acceleration. The frictional force, in this case, the maximum static frictional force, so I'll write that as F magnitude max, right? Because it reaches some maximum value until it slips into kinetic, and that's when this crate would start to fall off the back of the flatbed. This is in the positive direction, it's in positive x. The weight in x is in the negative direction, so I'll say minus weight in x equals mass times our acceleration in x. Notice this acceleration in x is our acceleration along the incline, which is the acceleration of the truck. So this value right here, acceleration in x, is the same as this value here. In other words, our maximum acceleration that this truck can have is the same as our acceleration in the x dimension now that we've tilted our axes. The second thing I'll say is that we know what weight in x is. We found that weight in x using a little bit of trigonometry down here, mg sine theta. Before we make any substitutions, however, I'm going to look at our forces in the y dimension. The forces acting in the y dimension, I look at my free body diagram, I see only two. I see weight in y and normal force. So we have the normal, which is in the positive y direction, and weight in y. That equals mass times our acceleration in y. Our crate is not accelerating perpendicular to the surface. It's not accelerating perpendicular to the surface, so it's in equilibrium in the y dimension. Therefore, the net force is 0. Our normal force is positive. Our weight in y is in the negative direction. So we conclude that the normal force is equal to weight in y, which is equal to what we said down here, mg cosine theta. Mg cosine theta. All right, we know the normal force, which is the same as weight in y, which is mg cosine theta. That is helpful because we're going to need to substitute that into this force of friction maximum because we know normal force is inside this equation. So we need to do a little bit more analysis here, and that should give us our answer in order to find the acceleration along the x dimension. All right, I'm going to rewrite this as frictional force, max, minus weight in x equals our mass. Now I'll do a simple substitution here of our maximum acceleration. Here's our maximum acceleration. The frictional force max, that is mu sub s times our normal force, minus whatever our weight in x is. I'll make that substitution. Our weight in x we found was equal to mg sine theta. Mg sine theta equals our mass times the maximum acceleration. Remember, this is the quantity that we're trying to find here. At what rate can the velocity of our truck change and avoid the crate slipping off of the back of the bed? As a pause here to understand what physics we're looking at here, what we're saying is that the frictional force here, which we see in our free body diagram, has to accomplish two tasks. That frictional force not only opposes the weight in x, or the x projection of the weight, so it not only supports the crate against the weight in x, it also is used to accelerate the object. Remember, net forces accelerate objects. So that's what we see here in this equation. We see that this is our frictional force, our static frictional force. What it's doing is it's overcoming our x projection of the weight, and it's generating some acceleration, doing both of those things. We would see that even more clearly if we added this to the other side. We'd see those are the two things that the frictional force is accomplishing: accelerating our object and supporting it, the crate, against weight in x. All right, a few more substitutions and we'll be home free. Mu sub s times, we know what our normal force is. We look at our calculations up here. We saw that weight in y was equal to mg cosine theta. We found that using Newton's second law in the y dimension. We found that normal force is equal to weight in y, which is mg cosine theta. So we can substitute in for normal force mg cosine theta, mg cosine of theta. This whole term right here, there's our frictional force now. That is the force that is accelerating and overcoming weight. We still have minus mg sine of theta here. Okay. And we have equals m. No new substitutions to make on this right side of our equation. What we notice here is that common to each term in this equation is the mass. Mathematically speaking, that means we can divide both sides of this equation by m, and therefore all of the m's will cancel. We can conclude here, therefore, that the acceleration, the maximum acceleration our object can undergo, depends on how big the coefficient of static friction is times g cosine of theta minus g sine of theta. This will give us the maximum acceleration that our truck can undergo. If we input our value of 0.350 here, and then gravitational constant on Earth, 9.80 newtons per kilogram, cosine of our 10 degrees, our g again of 9.80 newtons per kilogram, sine of 10 degrees again, we get our maximum acceleration is 1.68 meters per second squared along the positive x direction. In other words, if our truck accelerated any faster than this, say for example it accelerated at 1.7 meters per second, then the frictional force would not be sufficient to both overcome the weight due to the incline of this hill, right? And also supply a force necessary to accelerate the object. In that case, if the acceleration were 1.7 meters per second squared or greater, then this crate would slip off the back. However, if the rate at which the velocity of our crate we're changing is 1.68 meters per second or less, then the crate would remain in contact with the bed of the truck and it'd be able to safely ascend the hill. Let's briefly look back over everything that we've done here. We started with an image that showed an object, specifically our crate, that's traveling at some incline, at some angle, along an incline. Immediately our thoughts should be forces in two dimensions, especially because we're given an angle, a coefficient of static friction, which tells us something about forces, specifically a static frictional force, right? We should be thinking of some static frictional force here. And we're asked to find what acceleration is the maximum acceleration this crate can undergo. I know acceleration is related to this force here and the other forces that might be acting on the crate, so this is probably a forces in two dimensions sort of problem. Given that insight, we draw a free body diagram, tilt our axes to eliminate multiple components of the normal force, multiple components of the frictional force. The only thing we're left with is weight that has two components to it. If we look more carefully at the components of that weight force, weight is down, here's the y projection, here's the x projection. We know geometrically that this theta here, or the theta right inside there, is the same as our angle here, which in our problem was 10 degrees. We do a little bit of trigonometry and we find that weight in x, or the x component of the weight, is mg sine theta, and the y component, or y projection of the weight, is mg cosine theta. Then we do our analysis of Newton's second law in both the x and the y dimensions, based upon our new x and y dimensions, our rotated x and y dimensions. We find that frictional force is in the positive x, weight in x is in the negative direction. That equals mass times acceleration. We know this is not equal to 0 because we're asked to find at what acceleration along the incline can this crate move. We look at forces in y. We only have the normal force and weight in y. Normal is positive, weight in y is negative. The crate is not accelerating perpendicular to the surface, so its acceleration is 0. Its net force is 0. So these two must be equal to each other. Based upon our trigonometry, we were able to say that weight in y is equal to mg cosine theta. Finally, what we did was we merged these two analyses of forces in x and forces in y into our final equation at the bottom here. Rewrote force, the static frictional force, minus the weight in x, or the x projection, equals mass times acceleration. This is what we found using Newton's second law in the x dimension. And now it's simply a substitution question. Frictional force maximum is our equation for this force is mu sub s times normal. We know the normal force is equal to mg cosine theta. We know weight in x is equal to mg sine theta. Mass times acceleration still on our right side, second half of Newton's second law. With those substitutions, we can cancel m or divide both sides by m, and finally input our values of mu sub s at 0.350, g at 9.80 newtons per kilogram, cosine of 10 degrees, same g we just mentioned, sine of 10 degrees. Putting that in our calculator, we get the acceleration of 1.68 meters per second squared along the incline is the maximum acceleration our crate can undergo without slipping, or without the frictional force being too weak to support that acceleration. All right, thank you.